Welcome to the Oxygen Alliance YouTube channel, where we bring you videos on installation, maintenance, and various trainings on oxygen equipment and devices. If you have comments and/or questions, drop them in the comment section below or write to us info@oxygenalliance.org. Remember to like our videos, subscribe to our channel, and hit the notification bell.
Hello everyone, welcome to the Oxygen Alliance's Oxygen Talk, which is normally hosted every Thursday, 2 to 3 p.m. Central African Time. My name is Mwawi Lungu and I am hosting the call today from Lilongwe, Malawi. I am so happy to be hosting the call again after being on the sidelines for a while. So we are always excited to learn where each and every one of you is joining us from. So please share with us your name and the location where you're joining from in the chat so that we know where each one of you is joining us from. So today we are going to continue our discussion on understanding anesthesia technology. So in the first discussion that we had, we focused on the Gloucester-Vent anesthesia machine. And today our focus would be on the Universal Anesthesia Machine. So these are the two most common brands in most of the low and middle income countries. So that's why we are focusing on these. Speaking to us today are our biomedical engineers from OpenO2 and the Oxygen Alliance. So we have Grace Bwanali, Chimwemwe TSC, Foster Sentala, and Sharon Ngozo, ready to share with us an in-depth analysis on the UAM machine. So I will now hand it over to Grace, who kickstarts the conversation. So over to you, Grace.
Thank you so much, Mwawi, for that wonderful introduction. So, as already introduced, today we are going to focus much on the Universal Anesthesia Machine. So just a recap, an anesthesia machine is a machine that supplies a mixture of oxygen, gas, and anesthetic agent to a patient, allowing them to remain unconscious but breathing during surgery. So the device delivers oxygen while simultaneously ensuring that the patient does not inhale the exhaled life-threatening carbon dioxide. So this device is equipped with two modes. The Universal Anesthesia Machine is equipped with two modes, which is the draw-over mode as well as the pressure system mode. So the draw-over mode uses ambient air as a carrier gas for anesthetic agent, while the pressure system mode uses the oxygen supplied by the integrated oxygen concentrator or the external oxygen source such as pipeline and cylinders. So as you can hear, we have the oxygen concentrator that is integrated in this system, but also pipelines and cylinders can be used for the supplement of gases. Moving on, I'll take you through the parts and functions of the Universal Anesthesia Machine. So just over there, we have the patient vital signs monitor, which is the instrument that measures and displays the physiological state of the patient, and it primarily monitors the delivery of anesthesia. So distal to it, we have the low resistance vaporizer, a device generally attached to the machine, which delivers a given concentration of a volatile anesthesia agent. So it works by controlling the vaporization of anesthetic agents from liquid, and then it accurately controls the concentration in which these volatile agents are added to the fresh gas that flows through it. So below to it is the barrels, which is used for manual intermittent positive pressure ventilation. More of this part is going to be explained further as we go further with the presentation. And then we have the Fenton balloon inflation valve. This allows for controlling of inflation and deflation of the curve maintaining the appropriate seal while minimizing the potential harm to the patient's airway. Yeah, so after that part, we have the water trap. This there just to prevent the entry of excessive moisture into the breathing circuit. And then we have the integrated oxygen concentrator. As I've already explained, it's there for oxygen production. And then we have the pressure relief valve and the gauge. So on the other side, as you can see, we are pointing the gauge and also the pressure relief valve. So the pressure relief valve is just there to limit the pressures in the back bar to 5 centimeters of water, while the valves, the gauge is there to regulate the pressure. Moving on to the next slide, I'll show you the middle, just the middle parts of the Universal Anesthesia Machine. So we have the pressure relief valve, which is there to ensure excessive manual force of bellows cannot cause harm to the patient. And then we have the air inlet valve, which is there to allow room air to be drawn in whenever the supply of oxygen is less than the demand. We also have the reservoir bank, which is there to store the oxygen, and it holds up to 2 liters. Down to it, we have the nitrous oxide gauge, which is there to monitor the pressure of nitrous oxide gas. We have on the other side, we have the analyzer screen unit, which is there to display oxygen concentration in the gas mixture. This is the concentration that is being delivered to the patient, and this is also used for calibration. Below to it, we have the oxygen flow meter and the nitrous oxide flow meter. These are there to control the amount of these gases that are entering the back bar, and then that are also available for the patient. And then we have the oxygen pressure gauge. This monitors the pressure of the oxygen gas. I have the switch down there, the oxygen concentrator on and off switch. So this is there to control the oxygen supply. So it aids the switching on and switching off of the oxygen concentrator. On the back side of the machine, we also have these important parts. Next slide, please. Yeah, so we have the pipeline connections for oxygen and nitrous oxide gas. So these are used to connect the pipelines to the machine. And then we have the pin indexed connectors, the E-size oxygen and nitrous for oxygen and nitrous oxide. So these are used for connections with cylinders. And then we have the mains isolator, the on and off switch. So this is the main switch which is used to switch on and off the whole system. So down to distal to it, we have the electric outlets. So these are connections which can be used when you want to connect the machine to other electrical parts such as patient monitors. And then we also have fuses for oxygen monitor, oxygen concentrator, and socket outlets. So to this far, I'm going to pass on to my colleague Chimwemitias, who is going to take us through the power supply and specification. Also note that most of the parts that I've explained, their operations are going to be explained as we go further with our presentation by one of my colleague, Foster Sentara. Thank you so much. Over to you, Chimwemitias.
All right, thank you so much, Glenn. So I will take you through the power supply and specification. So the Universal Anesthesia Machine operates on a voltage of 220 volts AC with a frequency of range of 50 Hertz to 60 Hertz. So this machine is designed with a rated power of 500 watts. So this system features a medical grade control screen equipped with a backup battery of 12 which is an automatic voltage switcher. So detailed explanations of these components will be provided later in this presentation. So moving on, I'll talk about the standards of this machine. So this machine has a CE marking indicating its compliance with the general safety and performance requirements of the European medical device standards. So one thing that has to be noted is that this machine was designed specifically to adhere to ISO standard 18835. Which is for utilization in low and middle income countries where compressed gas and power supply may not be that reliable. So it can work in situations where you don't have reliable power supply and also when you don't have compressed gas. So my colleague Foster Sentala will explain better about this. So now we move on to the voltage surge protection. So this machine has an AVS, as I earlier hinted, the automatic voltage switcher that prevents damage to the machine from over and under voltage levels of any duration. So this works by disconnecting power when voltage levels exceed a set parameter. Actually, you do set the parameters on the the AVC. So reconnection takes place whenever the power returns to normal. So when you have voltage levels stabilized and there are no surges, you get the reconnection back. So to the right in the graphics, you have the AVS, the automatic voltage switcher. And to the left, that is, you have the automatic voltage switcher. And to the right, there you have encircled in red in the graphics, there are fuses that protect the concentrator and also protects this control screen and the socket outlets. So encircled in red, as you can see there, are the fuses. So moving on. So I'll now talk about the alternative power sources. So the machine has essentially 4 backup systems in case when there is power failure. So as I earlier said, we have a 12 horsepower battery which controls, which supplies power to the control screen. The control screen has oxygen analyzers and nitrous oxide cutoff valve connected to it. So there's also another backup, which is for the oxygen source. We have a cylinder backup, pipeline backup. These are the connectors that are located at the back of the machine. And there is also another backup in case of where you don't have an electrical ventilator. This one will use a manual ventilator using the bellows. So moving on, I'll talk about the electrical flow diagram of the Universal Anesthesia Machine. So electricity flows from the mains power supply to a voltage switcher, the automatic voltage switcher I area said. Then it goes to a mains isolator switch, which is located at the back of the machine. Then from here, in parallel, connected in parallel to it are the concentrators, a 12 volt, 24 volt power supply, and also an oxygen concentrator, and of course, 2 outlets where you can connect other appliances to it. So from the power supply, 24 volts power supply, the power goes to the control unit where an oxygen sensor is connected, and also we have the nitrous oxide cutoff valve, and also there is a speaker to it connected to it. So as you can see in the graphics as well, there is a battery, 12 volts battery, which is 1200 milliamp hour. So this battery supplies to the control screen in cases of power failure, as I earlier said. So we have the concentrator, and we have in the front a switch which is used to turn on the concentrator. So I'll move on to talk about the screen, the analyzer screen. And the graphics, you can see on the touch screen, we have the cow button. That's a calibration button setting to calibrate oxygen and apnea alarm. We have oxygen, a high oxygen alarm, a sensor where you can see high and 99 there. which can be adjusted by the user when they want to set alarms, and also when they want to do calibration. So we also have a percentage of oxygen shown in the graphics. You can see there where it is showing 64% oxygen. This is measured before inspiration, the gas before inspiration. So it shows you the actual percentage of oxygen for the carrier gas. We also have a mains power indicator and a pinion alarm, as you can see in the graphics. There is also a low oxygen supply, a low oxygen alarm button there, as you can see, indicator 18, and then below it there is 18. So moving on. I'll talk about the analyzer's clean unit circuit board. So there are several components that are connected to the analyzer's clean circuit board. It has the oxygen sensor, which is connected to part 3 via a cable. As you can see in the graphics, that part labeled 3 in orange is the part where the oxygen cable sensor goes. There is a pressure transducer. You can see in the graphics as it is indicated 4. You have a cable, a tube ladder carrying gas that carrying a pressurized gas that the pressure transducer measures. So there's also a speaker unit connected to part 6 via a cable. You can see in the graphics. There's also a touch screen unit connected to the board via a cable. So this part is connected to part 10. There is a display unit connected to part 11 via a cable as well. And also we have the power supply connected from the battery, the 12-volt battery, the backup battery connected to part 5. And also there is the nitrous oxide cutoff solenoid valve assembly unit, which is connected to part 7. So reaching this far, I'll hand over to my colleague Foster to continue with the presentation. So thank you so much.
Well, thank you very much, Grace and Chimwemwe, for introducing us to our model of focus today. I'll proceed with the presentation, taking the path of the pneumatics. So to begin with, our machine has been categorized into 4 main parts. These are the gas supply, the flow control, the vaporizer, and finally the breathing circuit. So in the gas supply, we have 3 main types of supply systems. So gas, in this case, oxygen or nitrous oxide, or in other cases, air, medical air, can be supplied either through pipeline systems or cylinder systems or the integrated oxygen concentrator, as it was pointed out by Grace. From this point, we have now the control for the flows. So we have the flow meters. We also have the indications for flow and pressures by the gauges and the regulators. We also have the roll resistance vaporizer, which is basically there to convert the liquid anesthesia agents into gaseous form to form the anesthetic gas. From there, we have what is known as a patient breathing circuit. This is there just to deliver the gaseous mixture to the patient airways and also to allow for ventilation. So I'll discuss more about the breathing circuit in the following slides. Moving on, I have also divided the pneumatic system into 3 categories based on pressure distribution. So the first part is where you have a high pressure system. This is covering all the parts that are accessible to the cylinder pressures. So if you're dealing with cylinders, you are working with high pressures. So all the parts that are accessible to the cylinder pressure, these are categorized into the high pressure systems. We also have an intermediate pressure system. This is covering the pipeline sources, the oxygen concentrator source, as well as the regulators and the flow controllers. We also have the third part, which is a low pressure system. So our model uses what is known as a low resistance system. So the vaporizer is a low resistance system. So you are dealing with gases flowing at low pressures. So if you're using a cylinder, for example, you have to reduce its pressure to a lower value so that you should be able to vaporize the anesthetic gases. This is so because this machine was designed for low and middle income countries, whereby there is no that good supply of oxygen. So it's basically using the oxygen concentrators and in other cases, ambient air. Moving on. This is just a pictorial representation of what I was talking about. So painted in red, that is the region where you have the high pressures. So you have your cylinders, the pressure gauges, and the regulators. And painted in green, that is intermediate pressure systems. And to the far right, in blue, that is the low pressure system, comprising the vaporizer, the flow meters, and where you have the outlet of your gas. Moving on, I'll also explain to you mechanisms that have been put in place to make sure that you have a controlled amount or concentration of oxygen being delivered to the person. So there's actually a sensor for oxygen concentration. So in cases whereby concentration of oxygen in the gas mixture falls below 25%, the control panel triggers the nitrous oxide cutoff valve to close. In this way, you are limiting the amount of nitrous oxide being delivered to the patient. And when it is closed, then gradually the concentration of oxygen regains its upper levels of concentration. So there's also an alarm system that usually sounds when you are accumulating pressures lower or higher than the normal pressures that you're working with the patient. So you actually set these pressures using the control screen as it was pointed out by Chimwemwe. So you have two mechanisms. One is monitoring the pressure. The other one is monitoring the concentration of oxygen in the gaseous mixture. Moving on, I'll now discuss about the ventilation modes. So our machine, the UAM, supports, apart from the spontaneous breathing from the patient, the normal breathing, it also supports manual ventilation as well as automatic controlled IPPV, the intermediate positive pressure ventilation. So as you can see from the diagram, the part labeled 1, that is the bellows that are used for manual ventilation. So when you have gas flowing from the machine to the patient, there are two valves that are placed before and after these bellows. So during spontaneous breathing, the first valve before the bellows open, and these are one-way valves, the unidirection valves. So when this valve opens, gas mixture is filled into the bellows. And during inspiration, the second valve also opens, and the gas flows freely from the bellows going to the patient through the inspiratory limb. And when the patient is expiring, the gas does not go back to the bellows. Now it takes another path, which leads to the Fenton balloon filling valve. So this is a valve that opens to the atmosphere, or the scavenging system, if you want to extrude the gas to the atmosphere. I'll explain more about this in the following slides, but this is basically the modes that the modes of ventilation that the machine supports, the manual ventilation as well as the automatic ventilation. So if you have an optional ventilator, you connect it on port labeled number 2. The newer models of this machine come with an option ventilator that also has a battery backup and can last to about 6 hours of use on battery. Just a point to note, this model of anesthesia machine does not have what is known as an oxygen flash button. Rather, it uses the same bellows of manual ventilation to achieve the same purpose. Moving on. I will now explain about the patient breathing circuit. So this is basically a breathing system, which is just an arrangement of tubes and other components that transport the anesthetic gases between the machine and the patient. So as you can see on the diagram, it is comprised of a fresh gas inlet. This is coming from the vaporizer. And you have the Y piece that is used to supply the gases to the patient. So you have one limb that is for inspiration and the other limb below it that is for expiration. So within these limbs, those are the unidirection valves I was talking about. So during inspiration, the upper valve opens, and during expiration, the lower valve opens while the other one closes. In other systems where you have a rebreathing circuit, you also have the carbon dioxide absorbers so that it traps the carbon dioxide that is being expelled from the patient. In other cases, you will have to add the ventilator to assist the ventilation to the patient. So other models, the ventilator usually is just a mechanism of squeezing the reservoir bag. So you have that reservoir bag that temporarily stores the contents of the gas, either from the patient or from the fresh gas inlet. So to assist in ventilation, the mechanical ventilator usually is used to squeeze this reservoir bag. This is why this kind of model just uses the bellows for ventilation. So the bellows represent this reservoir bag. So during inspiration and expiration, contents on the reservoir bag, in this case the bellows, are just squeezed out to be provided to the patient as a matter of assisting the patient ventilation. You also have what is known as an APL valve, which is an adjustable pressure limiting valve. This is put in place just to minimize the high pressures that can harm the patient. So in cases whereby you have high pressures building inside this circuit, this valve is used to release that excessive pressure to prevent the patient from being harmed. So this is also where you connect a scavenging system just to control how you are excreting the gas from the machine to the atmosphere. Moving on. So this is a simpler representation of what I was talking about. So on point number one, that is where you have the gas source. This can be the cylinders or oxygen concentrate and the likes. And then this gas passes point number two, which is a vaporizer, getting mixed with a volatile agent and then being supplied to our circle or our circuit. On three, that is the inspiral valve, and on point number five, that is the expiral valve. And on six, that is where you have the reservoir bag, and in our case, that is where the bellows are put, and that is also where you connect the mechanical ventilators. On 8, that is where you have the carbon dioxide canisters. So yeah, moving on. These are just pictures from our machine of focus today. So the left picture, those are the bellows for manual ventilation. And behind it, that is where you have the first valve, the one-way valve, and you have another valve after it. So during spontaneous breathing, all these valves open on inspiration and close on expiration. And below these parts, that is where you have the Fenton balloon inflating valve. So during inspiration, this valve gets inflated. In that way, it blocks the airflow so that you don't have air leaving the machine before it reaches to the patient. But during expiration, this balloon deflates allowing air to leave the machine to the scavenging system. To the right, that is where you have the Y-piece, represented as the inspiratory limb and the expiratory limb. So that is where you connect your patient. And on top of it, that is where you have the pressure relief valve. Moving on. So basically, this is a schematic diagram representing how gases are flowing in our machine, the UAM. So you have the oxygen concentrator as a source of gas passing through the pressure controls, and then this goes to the vaporizer after passing also the 2 liters reservoir bag. And also take note that these are monitored by the oxygen sensors and the cutoff valve for the nitrous oxide. So after the orange tube, that is at the end of it, that is where we are now entering the patient breathing circuit. So that is where you are tapping the fresh gas flow into the patient breathing circuit. Those painted in black, those are the bellows, and the other ones, those are the one-way valves. So this is a basic representation of how gases are flowing inside the machine, going to the patient and back, and then going out of the machine through the scavenger, passing the balloon valve. Finally, I'll handle some of the things that you have to check before you start to use the machine, or if you are using the machine between patients. So it is recommended that you have to calibrate the machine at the start of every operating session. So the most important things that you have to calibrate are one, the oxygen sensor and also the pressure sensors. So to calibrate the oxygen sensor, you use 2 ways. The first way, you use 100% oxygen supply. This can be a cylinder or either a pipeline source. So to calibrate using 100% oxygen, firstly, you have to set the oxygen flow using the flow meter to at least 6 liters per minute. So you have an adequate flow of oxygen into the machine. So you have to check the analyzer screen that it should lead a maximum value. And when you get the maximum value on the screen, that is when you press calibrate, represented as CAL on the screen. Then you select oxygen, then you click on go. After calibration is done, then to exit, you click the exit button twice. The same procedure can be done using room air in cases whereby you don't have 100% oxygen supply, whether you're using an oxygen concentrator or the machine is operating on draw over. So you have to calibrate using room air, 21% calibration. So you have to turn off the oxygen flow, and then you let room air get drawn into the machine using the manual bellows, as I earlier stated, during manual ventilation. So then you click calibrate, then you choose air in this case, then you click on go. After calibration is done, to exit, you click the exit button twice. That is how you calibrate the oxygen sensor. Secondly, on the next slide, if you want to calibrate the pressure sensor, the apnea alarm pressure sensor, so you set the values, the flow to 0. So you close all the flow meters so that you don't have any flow, and also you empty the reservoir bags. And then when you have no flow, you press on calibrate, then you choose pressure calibration as represented there, and then you click on go. And also to exit, you click the exit button twice. Moving on, the final thing that you need to check is if the nitrous oxide cutoff valve is working perfectly before you administering anesthetic agents to the patient. So you don't want to have cases whereby you are overdosing your patient with nitrous oxide. So to check this valve, what you do is you set the flow of oxygen to at least 6 liters per minute, and you also open the nitrous oxide flow to at least 4 liters per minute. So you have both flow for oxygen and nitrous oxide. When you have these two flows, then you gradually close the flow for oxygen. In this case, you are now decreasing the concentration of oxygen in the gas mixture going to the patient. So the system should be able to sense that there is a decrease in the concentration of oxygen. And in this case, when the concentration falls below 25%, the concentration of oxygen in the gaseous mixture, then the nitrous oxide cutoff valve should be closed, not to let any more nitrous oxide to flow into the machine. So this is how you check whether the nitrous oxide cutoff valve is working correctly. I will stop from this end, and then I'll let my colleague Sharon to take you through the last part of our presentation. Thank you very much.
Thank you very much, Foster. My name is Sharon Gozo, and I'll be taking you through the last part of this presentation. We'll be discussing about the problems that you can face when working with the UAM, and we'll discuss about the possible causes and some of the solutions. So the first problem that you can encounter might be where you have the oxygen concentrator and the control screen not turning on. So if you're facing this problem, some of the possible causes might be that the switch, this is where we're looking at the mains isolator switch and the oxygen concentrator switch, might be turned off. So all you have to do is turn them on. Another cause might be that maybe you have some voltage instabilities or even power surges. So in this type of scenario, what you have to do is to use a voltage stabilizer. Another cause of this problem might be a faulty socket outlet, or you have malfunctioning of the mains isolator switch or even the voltage switcher. Another cause might be a broken mains plug or cable that you just have to check it and then you fix it. Or even if you're using a voltage stabilizer between the UAM and the wall socket, if that voltage stabilizer is malfunctioning, it can also cause this problem. The second problem we'll look at is where you have the UAM shutting down and restarting. So this can be caused by voltage instabilities. So all you have to do is use a voltage stabilizer. Or if you have a fault in your local wiring, you have to check it out and make sure that it is fixed. Another problem might be where you have the oxygen concentrator not turning on, or you have a noticeable hot smell. So this can be a result of a blown fuse. So it uses the 5 amps fuse. So all you have to do is check it out. If it is blown, make sure you repress it. Or the following malfunctioning of the following things might be the front switch or the mains isolator switch, or even the voltage switcher, or even the circuit board for the oxygen concentrator. So you need to check this out. Or even when you have the compressor failing, they can also cause this type of problem. The other problem we'll look at is where you have the analyzer screen not turning on. So this will be caused by a blown out 24 volts power supply unit fuse, or if you have a defective 24 volts power supply unit. Even when the circuit board is failing, they can cause the analyzer not to turn on. So all you have to do is to check them out. If they need to be replaced, make sure that you replace them. Moving forward, the other problem you can encounter might be the oxygen analyzer displaying 104% at higher oxygen concentration. So in this type of scenario, the causes might be the oxygen sensor needs to be calibrated with 100% oxygen. So my friend Foster mentioned about calibration. So make sure that if you're calibrating the oxygen sensor, it's either you're using the oxygen source, which can be an oxygen concentrator, or you're using oxygen from a cylinder. So if you're using oxygen from the cylinder, make sure that it is 100% pure oxygen. Because if you're using anything less than 100% and you're using that to calibrate the sensor, then it is more likely for you to be getting this kind of purities on your display. The other problem you can encounter is where you have the oxygen sensor will not calibrate, or the monitor readings are erratic. So the causes might be that the oxygen sensor is exhausted and all you have to do is to replace it. Or the oxygen sensor, the cable is disconnected or it's broken. So you have to check it out. If it is disconnected, make sure you connect it back. or if it's broken, then you must replace it. The other problem we'll look into is where you have the audible alarms not working. So the causes of this might be that maybe the speaker connector is disconnected, which just needs to be connected back, or where you have the speaker malfunctioning and it has to be fixed, or where we have the malfunctioning oxygen, we have the malfunctioning analyzer screen circuit board. So this needs to be fixed. The other problem can be where the analyzer screen shuts off when mains power is lost. So here you have to know that you have a battery that works with this. So you need to check the battery if it needs recharging or if it is disconnected. Sometimes it might be that the battery has lost its capacity to charge, and all you have to do is to replace the battery. Moving forward, the other problem you can encounter might be that the nitrous oxide does not cut off when oxygen percentage is less than 25%. So with this type of problem, the cause might be that the cutoff solenoid valve is malfunctioning, or even the analyzer screen circuit board is malfunctioning. So you have to check this. If they're malfunctioning, make sure that you clean them up or you replace them if need be. Moving on, the other problem is where you have the apnea alarm does not activate. So with this type of problem, the causes might be that maybe the mute option is selected. So you have to make sure that you unselect the mute or the mute is off. The other cause might be that where you have the pressure transducer needs to be calibrated. Or you can have the analyzer screen circuit board malfunctioning. So you need to check it. The other problem we'll look into is where you have the oxygen concentrated output measuring less than 90% purity. So if you have this problem, the causes might be the oxygen sensor needs to be calibrated to both 100% and 21% oxygen. So make sure that if you're calibrating with the 100% oxygen, you're using the cylinder and you're sure that the oxygen is 100%. The other cause might be the malfunctioning of the water trap in the oxygen concentrator, where this allows moisture to saturate the moisture in the zeolite cylinders. So all you have to do is to clean it, or you can replace it if need be. The other cause is where you have the air filter is dirty and is obstructing the airflow. So you need to clean it up, or if it needs replacing, then go ahead and replace it. The other cause might be where you have the air compressor malfunctioning. So you need to check that. Also, you can have the switching valve malfunctioning. So you need to check these and fix them. The other problem we'll look into moving forward will be the oxygen concentrator output does not reach the 10 liters per minute, or the flow is fluctuating. So with this type of problem, you have to adjust the concentrator's output regulator. So make sure it's adjusted to the required pressure. The other problem we'll look into is where you have the concentrator alarm not active when power is lost. So one thing we know is concentrators have the 9-volt alarm battery. So you have to check if the battery is disconnected or if it's discharged, and you need to replace with a new 9-volt battery. The last problem you can encounter is where you have the breathing system pressure too high. So with this one, you have to check the pressure relief valve. It might be that maybe it's not opening. So all you have to do is remove it and clean it up, then you depress it back. Or you can have the balloon valve malfunctioning. So you do the same again, you remove it, clean it, and put it back. Or else if it needs replacing, then you go ahead and replace it. So reaching this far, this is the end of our presentation. Thank you.
Right. Thank you very much, Sharon and team, for that wonderful presentation. I'm sure we have learned a lot. And now, looking at the time, we still have like 14 minutes to the end of the call. So I will now invite questions and comments from the audience. So if we have any questions, you can either raise your hand, or you can paste the question in the chat and I'll read it out, and then one of the engineers will respond to that question. So The floor is open for questions now. Yeah, we have a hand from Robert. You can come off mute and ask your question.
Yeah, thanks very much for the presentation. It's quite informative. I did wonder when you mentioned about the 100% oxygen, that we know that some systems, even when they are made to deliver 100% oxygen, they don't really. Is this something you've encountered in your practices, and what do you do? I know that it was mentioned also during the presentation that you need to ensure that it's 100% if you are using 100%. And also maybe as a sub question is, have you had challenges where your analyzers, oxygen analyzers, are the problem and they are not giving the correct result? Thank you.
Thank you, Robert. Sharon and your team, I think anyone can take this one up.
Okay, thank you very much, Robert. I'll take the first question where you're asking about calibrating with 100% oxygen. So during this type of calibration, what you are doing is just you are setting the maximum limit, the maximum value that you can achieve with your gaseous sources. So it is recommended to use pipeline supply because you know you have higher oxygen concentrations above 95%. So you can go up to 98 or in other cases 99%. So what you're doing on this calibration, you're just setting the maximum value. So you're telling the sensor that if you have this value, this is the maximum that you can get, in this case 100%. Or else you are setting, if you're calibrating with room air, in this case, you are telling that if you have this type of air, this percentage is 21% oxygen. So yeah, there are cases that you can't reach 100%, but you just have to make sure that the source that you're using to calibrate is the source that has the maximum concentration of oxygen. I hope that answers your question.
Sorry, I don't know if I can come back and maybe clarify what I was asking.
Yes, please, go ahead.
Yes, I was asking about your experiences, because my experiences have been that even systems that are meant to give us 100% oxygen don't necessarily do that because of so many challenges. We found in our local hospitals here that even the plants that we have that are meant to give us 100%, when we measure, it's much, much lower. So I'm asking from your experience perspective, that is this something you've encountered, and how does that affect your calibration?
I've got your question. Yes, you are right that we have also experienced cases whereby you don't actually get 100% of oxygen concentration from either the pipeline sources or from the cylinders. We also had a case, I think Chimweme can also add on this, whereby he experienced a concentration of even lower than 80% from a pipeline source. So yes, you are right. So my point was, in cases whereby you have analyzed your gas source that it is lower than 100%, you have now to use the room air calibration. So this is important to use when you have cases whereby you know that your source of oxygen is not cannot go above 90% or cannot reach 100% of purity. So where you have these cases, that is where you can use the room air calibration. But yes, I agree with you. There are several cases whereby the gaseous sources cannot provide a higher percentage of oxygen, up to 100%. Yes.
Okay, great. Thank you, Foster, for that. I hope that answers your question, Robert. If you have any more follow-ups, you are free to bring those up. So we also have a comment in the chat from Rock Musoli, which says, During calibration, you have to check for leakages in the pipeline and the bellows housing. So I guess this is also something that you would need to pay attention to when you are doing your calibration. I see we have a hand from Chimwemwe. Is it responding to the same? So actually, we also have one outstanding question from Robert about the oxygen analyzers. So Chimwemwe, if it's relating to the same, then you can respond to that.
All right. I wanted to mention about the analyzer. You may have issues with calibration of the sensor. So if the calibration is outdated or there are other issues with the sensor, like aging electrodes inside the sensor, you may get false oxygen readings from the sensor, sometimes going over 100% or maybe below that because the sensor is not okay. So what you need to do is to check with another sensor, just do the comparisons, maybe to see which one is giving the expected oxygen readings from your oxygen source. So that's what I can say for the analyzer. So this one is specifically about the electrochemical analyzer. You may also get issues with the sensor if you're using a ultrasonic oxygen analyzer. So I hope that answers your question, that we have issues indeed with sensors, which is mostly due to calibration issues. So thank you.
Yeah, thank you. That answers my question, both of them.
Okay, great. Anyone else who has a comment, you are also welcome to make that comment. We have a hand from Paul Fenton. You can come off mute.
Hello, yes. I saw in the diagram you showed a circle system with a CO2 absorber. Of course, the Universal Anesthesia Machine doesn't have that.
That's correct.
So isn't that rather confusing?
So it should not be that much confusing, because I also stated earlier on that this diagram represents a rebreathing circuit, but our model, the UAM in focus, does not use rebreathing system. So when the patient is expiring, all the gases are directed to the scavenging system via the Pfaff-Fenton balloon filling valve. So yes, the UAM does not use a rebreathing system. So this was just a general explanation of how the other models incorporate the use of rebreathing system.
Okay.
Yes, and thank you very much, Paul, for joining the call. I believe the valve, the Fenton filling valve, was named after you. So we are delighted to have you join this call.
Yes, thank you. That valve was devised in Malawi, by the way, so something worth remembering.
Okay, well, thank you very much.
All right, we have another hand from Jerry. You can come off mute.
Thanks. So maybe a follow-up question for Paul. So given that some devices do use CO2 scrubbers and the UAM does not, what were the kind of considerations there for that? I understand that the CO2 scrubbing technique is not something that is reversible, right? You need to continually change the material. Was that one of the considerations for not incorporating CO2 scrubbing into the UAM design?
It's a long story going back a long way, Jerry, but the very first prototype in the late 90s for the forerunner of the UAM did have a CO2 remover. It didn't work out very well, and there was a problem with renewing the agent all the time. And I was trying to get manufacture in the UK, and to keep it simple, we didn't have any kind of recycling of expired gases. It was to be a Mark II project that I wanted to get on the road, but it never happened. So we're remaining now with a simpler system of the UAM as you see it today. So it was something on the drawing board that never happened.
Great, thank you. And I just saw a comment from Deb, and I'd like to comment on that, and maybe also a follow-up on Robert's question. I think generally we have struggled with measuring oxygen concentration. We primarily have used two of the different oxygen analyzer technologies, the ultrasonic analyzer and the electrochemical analyzer. And one of the challenges with the ultrasonic analyzer is that the approach that's used is used to concurrently measure flow rate as well as oxygen concentration. And at certain fixed flow rates, it does a fairly decent job, but it is a moving target. So it's continually checking itself to see whether it's found a balance between the flow rate and the concentration. Has Deb pointed out that certain devices will not go above, I guess it's 95.6, which is the theoretical upper limit for when we remove all nitrogen and we're left with all other remaining gases. So 95.6, many analyzers will not go below 21 and will not go above 95.6. So we tend to see kind of like a false ceiling in some cases. We think it's 95.6, but it could be 96 or 97, or it could be 100, and it's only going to display 95.6. The electrochemical ones, in theory, are not subject to this challenge of measuring, trying to concurrently measure flow and purity at the same time, and can potentially, I guess, go all the way up to 100%. And we've certainly seen challenges with some of the MaxTech devices. I think we have 3 different models here that we use. We're always trying to compare them and try to understand the relative differences that we're seeing with one source of oxygen getting 4 different readings from four different instruments. We're occasionally getting readings where it is going above 100% as well. So I think it's particularly challenging. We're looking for accuracy in the 1 or 2% range. So just a couple of closing comments there.
Okay, great. Thank you very much, Jerry, for those additional comments. I hope that also helps to clarify on those issues on the oxygen analyzer. And thank you, Deborah, for your comments as well in the chat. I hope with Jerry's comment that has also clarified. Do we have any other questions? We have reached the hour mark and we need to wind up the calls. Maybe someone has one last question. We can just take one more. All right, silence means we don't have any more questions. So this now brings us to the end of our call today. And I would like to thank the Oxygen Alliance and OpenO2 team for the wonderful presentation. It's really been informative. And thank you, everyone, for joining us. One quick reminder, if you want to join our emailing list so that we should be sending you updates on the content that we produce, reminders on when we have the next call, please drop your email in the chat and we will add you to our emailing list. So remember that these calls come your way every 2nd and 4th Thursday of each month. And we also sell in the email reminders. So as I said, please share your emails with us. And our next meeting will be on the 24th of August. So please put that on your calendars. And we'll also be sending out invites. So please don't forget to share your email addresses with us. We have a Facebook page. Please like it. We have a YouTube channel. Follow it. If you happen to have missed the first part of the presentation, you can always catch up from our YouTube channel. I also just wanted to say thank you, to acknowledge one of the our colleagues who we have been working with from Gradient Health, Kenneth Otieno. He helped us to clean up the presentation and everything. Unfortunately, he didn't join, but I'm sure he's going to watch the recording of this. So reaching this far, thank you all for joining the call, and we will see you again in our next talk. Thank you. Bye.